Good afternoon, dear workshop participants. I represent the Space Research Institute, Moscow, and in my presentation I will be discussing our experience in large-scale forest monitoring in Russia using Earth observation data. The main components of large-scale forest monitoring are as follows. Earth observation data archive, which is updated automatically in near real-time regime. And this archive contains different satellite data from various sources. Automated Earth observation data processing change, including Earth observation data pre-processing, and thematic products generation, such as land cover, forest species, growing stock volume, active fires, burnt area and severity, and others. Web-based users interface, which provide access to data for users and also provide data analysis tools and analysis of thematic data. An important component of large-scale forest monitoring is the availability of satellite data to the study area. Our data archive includes the following Earth observation data: MODIS data, Landsat data, ProBV data, Sentinel-2 data, KMSS data, and others. Here you can see examples of satellite data coverage available in Data Archive. Images obtained from the Vega Online service. The MODIS data, which are updated in daily regime. Landsat coverage for the period from 1st January to the beginning of March. There are data only for the beginning of current year. And Sentinel-2 data coverage for the same period. If we're talking about large-scale forest monitoring, there are some requirements and limitations which you must consider. First of all, the high level of data processing. If we want to regularly receive thematic data over large areas, we must use automatic approaches. The second requirement is local adaptability of approach and methods. For example, the large forests in Russia stretch from north to south and have different spectral properties. And if we want to map them, our approaches should be automatically customized for different territories. The next requirement is high temporal resolution of Earth observation data. Data with high frequency of observation, for example with daily frequency, provide additional information. You can receive information not only about spectral properties, but also information about how these spectral properties change during the vegetation season. And the last basic requirement is availability of long-term time series of Earth observation data. Long-term time series provide the ability to receive information about the average annual spectral properties, about their interannual changes that is important for change detection, and thematic data derived from long-term time series allow to get long-term data on the dynamic of vegetation and its properties that is important for trend analysis. At the present time, MODIS data meet these requirements. MODIS data have daily frequency, global coverage, and long-term archive since 2000. These data are widely used for large-scale monitoring technologies and automated methods. I will focus my presentation on MODIS data processing, but presented technologies and methodology can be applied to other Earth observation data. An important component is data pre-processing. On the first step, we detect cloud and shadow pixels. We use two different schemes for summer, it means snow-free, and winter data. To detect clouds on the summer data, we use blue channel and NDSI index. Snow pixel also detected and filtered. And to detect shadows, we use sun sensing geometry from metadata to identify all potential shadow pixels, since we don't know cloud height. And then we use reflection threshold for more accurate identification of shadow pixels. For winter data, we use sphere and blue reflecting space. The main difference is that we do not need to filter snow pixels, cause in winter data most of pixels are covered by snow and they contain useful information. After data pre-processing, we can implement time series reconstruction algorithm. We have individual measurements during vegetation period, and we can make serial of polynomial approximation within moving window, and then calculate average values for each day. So we can receive synthetic daily reflectance measurements time series. After preprocessing, we can receive seasonal composite images that use full-length cover mapping. 5-day composite images for forest species mapping and daily images for burnt area and severity mapping. Here you can see the examples of modest cloud-free seasonal composites for spring, summer, autumn and winter that used full-length cover mapping. A few words about locally adaptive global mapping algorithm LAGMA developed in IKEA. The main idea is to divide the territory into cells and to perform classification for every cell using local spectral temporal signatures of classes. Here you can see different cells. One contains a lot of sample data, another contains a little. If the number of reference pixels inside the cell is less than threshold, algorithms start to expand area for signature collection. The thresholds are chosen in such way that for neighboring cells, the signatures are collected from almost the same area. So the signatures of classes for neighboring cells change slightly, and it allows to avoid border effects. But for very remote cells, signatures can be very different depending on local features. Here you can see land cover map derived using LAGMA approach. This maps has over 30 classes, including 8 forest classes, and these maps are updated with an annual frequency. The next thing is forest species large-scale mapping. The method also uses local adaptive approach, but instead of 4 seasonal images, use time series of images with 5-day frequency. Here you can see the trajectories of different species in red-Nile reflectance space from the beginning of vegetation season to the end. And these temporal features also used as additional information for classification. Here you can see the annual Russian forest species map with 24 species classes that was derived using seasonal time series of MOIDIS data. The growing stock volume estimation approach using winter data. The main idea that in winter we take into account 3 fractions: snow area, tree crown area and tree shadow area. The ratio of these fractions produces pixel brightness in red channel. The more crown and shadows in the pixel, the more growing stock volume of forest and the less reflectance in red band. In approach, we use the relationship between red channel and growing stock volume data separately for every forest species. Here you can see the map of growing stock volume in Russia. The use of technologies described above allowed obtaining long-term data on the forest of Russia. The slide shows the trend of changing forest area in Russia from 2000 to the present time. As you can see, there is trend to reduced forest area about 500,000 hectares per year. If we consider this data into the context of forest types, we can see that different forest types has different dynamics. For example, dark needle-leaf forests have significant reduction in the last 20 years, while other forest types have less dynamics. Another important thing I want to tell are technologies of large-scale burnt area and severity monitoring. We developed multi-resolution burnt area mapping approach that include active fire burnt area mapping. This is the most rapid burnt area product. Surface reflectance burnt area mapping, and these two methods are fully automated. And high resolution burnt area mapping. These methods have different spatial resolution of user data and different mapping rapidity. The first is active fire burnt area mapping. This approach uses hotspot data with aggregation of hotspot pixels into fire polygons. Here you can see example of fire area changes over time derived with hotspots data. The next approach is automated mapping using reflectance data. This approach uses SWI index that based on near and short wave infrared channels. The main idea that we have typical dynamics of SWI data in the previous 5 years and dynamic in current fire season. We detect seasonal anomalies of index, and on the next step we check if these anomalies match by time and by space with hotspots pixels. This is combined approach which allows you to map fires with a higher than hotspot data resolution. Here you can see the example. The green line shows mean values of SWI index dynamics. The blue line shows standard deviation. And the red line shows dynamics of SWI index in current fire season. You can see the fall of index after the fire, and values begin to show significant difference from the reference multi-annual data. The next approach is semi-automatic burnt area mapping using high-resolution data such as Landsat or Sentinel-2 data. Here you can see the coverage of Landsat data for Russia during 2018 fire season. As I said, this is semi-automatic approach based on web service Vega that provides access to remote sensing data and products along with mapping tools for burnt area mapping. User pick up cloud-free satellite data, makes route access fire contour, and start classification. Then select clusters that are related to the fire and enter the data into the database. Here you can see the example of burnt area assessment using different approaches. And there is approach for integrated burnt area assessment. For every single fire event, the most accurate burnt area assessment is selected. The next thing I want to tell is burn severity assessment. Assessment based on empirical relationship between vegetation index, RD-SWI, and tree mortality. You can see the modest derived Russia forest burn severity map with 4 classes of severity. These technologies allow to obtain some unique scientific data. The gray line shows multi-annual burnt area dynamic over Russia, and black line shows high severity and lost forest areas. And this data for Russia territory are obtained for the first time by EKI. And dotted line shows the percentage of tree mortality area in burn severity area. And you can see this parameter varies in a wide range in different years from 30% to 70%. We found that the percentage of dead forest depends on the seasonality of the fire. You can see that burnt areas have high values from May to August in Russia, but the greatest probability of fire-caused mortality is observed in summer months. The probability of tree mortality also depends on forest species and forest types. On the slide you can see statistical data of mortality percentage for different forest types. These data are used for tree mortality forecast depending on forest type and fire seasonality. As I said, presented technologies and methodology can be applied to other Earth observation data, not only for MODIS data, and we have some experience in regional forest mapping using ProBV data. Here are some examples of ProBV derived maps for Primorsky Krai region, land cover map, forest species map, growing stock map. And we're also looking forward for Landsat data mapping using the same technologies and methodology. Here you can see the example of Landsat cloud-free composite image. Another important thing is the system for providing access to remote sensing data and products, along with tools for data processing and analysis. For these purposes, we developed Vega service mentioned above. The system provides access to Earth observation data archive with data analysis tools. There are tools for image enhancement and color compositing. The tools for image classification, both supervised and unsupervised. Here's the example of supervised classification. You can see the training set created automatically based on Modi's land cover map and the result of land cover supervised classification that based on this training set. There are also tools for time series analysis. You can see the seasonal dynamics of vegetation index on logging areas, and you can see the lower values in a year after logging. This data can be used to date the forest changes. Thank you for your attention.